So first talk about really thermal data for cryovolcanism. I may be a bit biased, but I sort of feel like if you're going to look for volcanism and you're going to look for active volcanism, thermal data is what to use. So, I'll do this. So just to remind you a little bit about the observations of the Europa plumes. And Candy did a much better job doing this, giving more of the background than I will. But I wanted to concentrate on the source that Sparks et al. Found. Because one of the things I found most intriguing about this is not only that he saw it, they saw it repeatedly in the same location. They saw it twice in a very similar location. But I was very impressed that they then went and looked at other data sets to sort of see what else could corroborate the presence of a plume. And of course, on Enceladus, all the active plume sites are warm. They're very warm. On Io, my favorite moon, Dave's favorite moon, maybe, every active site is hot. So if you want to look for activity, you should look for the heat. And so this is from one of the better PPR, Galileo PPR maps of Europa. This is a nighttime thermal image. The contours are temperatures. And it's nighttime, so you do expect some re-radiated sunlight. But this is not the subsolar point, or I shouldn't say the subsolar point. This is not the point closest to the equator and closest to sunset, which is where you'd expect to see the warmest place at night. You'd expect it to cool off as it gets later and then toward the next day. And of course, you expect it to cool off toward the poles. And so seeing the warmest area in this entire map was at this location was a bit odd. It didn't match exactly what you expect. So John Spencer in a science paper, I believe it was, actually no, I don't remember what year it was, mentioned this as a thermal anomaly, but said we didn't really have good data to really say what it is. But the fact that it was in a very similar location, almost identical location to the Sparks observations, gave some credence to there being a plume there. And then, of course, there was this more recent paper folks haven't been talking about yet at this meeting. But this was a reanalysis of the Galileo data, looking at both magnetometer data and plasma data, and using a plume model to match those data. I don't know very much about the models or magnetometer or plasma data, but I did notice that the plume site that they found, which is indicated here, is very different than the site Sparks found, which is that green ellipse. It's about 1,000 kilometers away. Furthermore, it's nowhere near the thermal anomaly. So this is a better image of that entire nighttime map. You can see the time of day. So this would be dawn. So you'd expect the coldest temperature sort of over here. I would expect the warmest temperatures in this map to be, right around here. And there are some warm temperatures there. So you can see this is sort of a thermal anomaly. This point is nowhere near the thermal anomaly. It's way off. The temperatures are pretty much what I expect for that time of day. So there's really nothing in the PPR data at that location. Okay, this I put in here for fun. I should also point out that there's a high what's the word I'm looking for? High frequency component that is not plugged in here, because it does change on almost an hourly rate. And then after Candy's talk, it went a little up, and then so there's some high frequency stuff there that didn't quite make it. That's a funny Jeff's face on the next version of the plot. One cargo. Okay, so the PPR data, which not a lot of folks have looked at, we have, thermal maps of Europa in the daytime and the nighttime. The resolution is pretty low. Even our best images have a resolution of about 50 kilometers. So we didn't see anything that was like, the Sears data on the South Pole of Enceladus. Nothing just like jumped out as like, this is a hot spot. But in a 2010 paper, we went back and we looked to see what could be hiding in the data? What were the detection limits? So this is a graph from that paper. And this red circle indicates the sparks location, and the orange circle is the jaw location. And these, I had everything in units of like gigawatts and watts and stuff, but in order to make it sort of a little more interpretable, I said, what if you had a 100 square kilometer hotspot? And we came up with that number because people were looking at a lot of lenticulae at the time, and they seemed to have the size of 10 kilometers. So what if you had something that was 100 kilometers squared in area? What would the minimum detectable temperature be? So in this spot, if there were something warmer than 170 K that filled the pixel, or was, you know, substantially large enough. Actually, no, it doesn't fill the pixel. It has to be 100 kilometers square. What am I talking about? If this was inside the pixel, we would have seen it. The same over here, it's down to 140 K. So I can be pretty confident there isn't anything of that size, warmer than that, on the surface. So we do have some constraints from the PPR data. This just shows some of the best images from PPR. These are the daytime best images. The asterisks here are the subsolar points for the two observations. So you can see this. You know, you mostly get the pattern you expect. It's warmer at the subsolar point and cools off toward the poles and toward earlier and later in the day. This one also, but there's definitely variations, which is not surprising. There's albedo variations all over the surface. There's probably thermal inertia variations over the surface. And then here's our best nighttime maps. There's 3 of them here. Yeah, this one actually does a good job sort of showing you what I expect. I expect it to be warmer near the poles and near the beginning of the night, and cooler at the end of the night and near the poles. And there's our North Pwyll thermal anomaly, and here's the jaw point. One interesting thing, one really nice thing to notice here is that for this North Pwyll point, we didn't have a good daytime observation. So it really is hard to constrain the surface thermal properties if you don't have both a day and a night. However, for the jaw location, we do have both a daytime and a nighttime observation. So there are much better constraints on that point. So here is some work that we published in 2014 where we derived those thermal properties, the albedo and the thermal inertia. And what we did is with 9-degree bins on the surface, we looked through all the data, found a daytime point and a nighttime point, and as long as there were both, we could fit a thermal model. As I said before, the jaw location is pretty well defined. The Pwyll location was, we could do a thermal model, but there weren't good daytime points. There were really crappy daytime points. And they were all early morning. So the jaw location, we got an albedo of 0.4, thermal inertia of 100. And one other thing to notice is with the jaw location, it's not that different from the surrounding areas. It looks basically the same in thermal inertia and albedo. The Pwyll area here, the thermal inertia is substantially different than anything nearby. So there's something different in that area. So for the sparks location, we wanted to do a better thermal model because PPR didn't have great daytime data. As I just said a couple minutes ago, we did have some early morning observations, but they were in these less sensitive narrowband filters, very noisy, noise of nearly 10 Kelvin in those observations, so much noisier. And we had no midday observations. And really, it's the middle of the day where it's that peak of the diurnal curve, which really constrains the thermal inertia and albedo. However, ground-based to the rescue. I do like ground-based data. Trumbo et al. Published some ALMA observations that they observed this region. This is the North Pole region in the daytime. They found that it was colder than the surrounding terrain during the day, which suggests a thermal inertia variation, not endogenic heating. It was endogenic, you'd expect it hotter in the day and the night. And again, though, the thermal inertia is greater than the surrounding terrain, which is what I also showed in the PPR math. So we did some more thermal models because when Trumbo did her thermal models, she only knew of 2 of these data points. This is the ALMA point. This is the nighttime, the one with the really small error bar is the nighttime PPR point, and these are sort of those 3 with the big error bars I mentioned, the big noisy things. So we ran a whole bunch of thermal models trying to find something that fit. Our best model was having different emissivities at PPR wavelengths than at ALMA wavelengths, because PPR is about 30 microns, and ALMA is 1.3 millimeters. So those are substantially different. So let me give you some caveats on that thermal model. I mentioned the different wavelengths. So they probe different parts of the blackbody spectrum. This is a problem because you likely have a combination of temperatures. These are big footprints that we're dealing with. Also, they probe to different depths. Also, we're talking about completely different times. We're talking about even the Galileo observations were 650 days apart. Even the two Sparks observations were hundreds of days apart, and ALMA was hundreds of days apart from that. And in the Abramoff and Spencer paper, where they're looking at cryovolcanic flows on the surface and how they cool, they can cool substantially in that amount of time. So that's also going to mess things up. So does this mean, and this was just for the North Pwyll point, does this mean that there's no plume if there's no endogenic heating? And so we go back to my favorite place, Io, and we look at the Pele plume deposit, which of course Dave showed earlier, and we see that the temperatures in the Pele plume are higher than the background. This is a nighttime image, so that suggests a higher thermal inertia in the plume fallout, which could explain the higher thermal inertia in the North Pwyll, but it could also be explained by Pwyll ejecta. So this is a big problem. This is why my belief goes up and down. So this is, I went too slow earlier because this was the important part. Could a hotspot be hiding in these data? Because they are pretty low resolution. So I looked at the ALMA data, and this is their footprint size on the surface of Europa. And I just sort of calculated in the ALMA wavelengths what a brightness would be in the background at the temperature they measure versus the temperature of a hotspot. And it's a lot smaller. So there could be a hotspot hiding in the ALMA data. And then here is for the PPR data. And the footprint, 45 kilometers. So this is in gigawatts. The total brightness in a PPR footprint is 9.2. If you had a 100 square kilometer hotspot at 170 degrees, it would be 4.7. If you had a tiger stripe, a single tiger stripe, not all four, just one, which is at a temperature of 133, which is the Enceladus temperature measured by Sears, the brightness would be 1.5. The detection limits I showed on an earlier slide were 2 gigawatts at the JA location and 5 gigawatts at the Sparks location. So you could be hiding hotspots like this in the PPR data. This is why I go back and forth, because on one hand, you don't need a hotspot to fit the thermal data, to fit the diurnal light curve, but the footprints are so large that you could possibly be squeezing something in there under the detection limit. So this is for the Sparks location, some conclusions. Endogenic heating is not necessary. So even though I liked the fact that Sparks brought in the thermal data, it turns out it wasn't quite indicative as he would have liked, as some folks would like. However, the higher measured thermal inertia say something might be going on, although as it said, it could be due to the Pwyll ejecta blanket. Have to say, if we get e-Themis data, when we get e-Themis data, this is going to be great. Multiple wavelengths simultaneously will be able to differentiate all these different things, much higher spatial resolution. And then the JA location was much better observed by PPR than the Sparks location. I said most of this. It's not within the PPR thermal anomaly, which they actually say in the paper it is. That's incorrect. And nothing in our thermal data suggests this location is special in any way. It is not different from anything nearby, and it's way too far from the Sparks location to be the same plume source. It's a different one. That's why my belief went down recently, because it just seems like there's so many observations where people rush to think it's a plume, and I'd love to hear what I heard from folks yesterday and the first day of the conference, which were multiple working hypotheses that could explain the data. And a lot of these HST data sets, they just said it's a plume without looking at other possibilities, is my opinion. So I'll stop there and let people yell at me.
Hi, Julie. Thanks. I just had a question about the Clipper trajectories and things related to, I guess, is there, I know I work on the project, but like I actually don't know. Like, I mean, do the trajectories line up, or the trajectory, the flybys, do they line up at all with like going over and getting that higher resolution ETHEMIS data at these areas that are in question? Or that
my understanding is Pwyll is hard to get to. I see Jeff knows the answer to this, I think, better than I do. But Pwyll is hard to get to because it's on just the wrong point. But the ETHEMIS data, even when we're going to look with ETHEMIS when we're further away than what most of the instruments are looking at, because if there's a hotspot, we're going to see it further away, and we're going to get data both at daytime and nighttime to better constrain this. Yeah, so even though we're not getting great resolution over Pwyll and flying by close, we're going to get Pwyll with ETHEMIS with enough resolution to do this better.
Yeah, I mean, we'll never fly close on top of it, but it's going to be plastered with ETHEMIS scans because it's in exactly the right location to keep scanning it over and over again. So, yeah.
So we'll get multiple times a day. We'll have multiple wavelengths. We can do this so much better.
Hi, I have a question that's just going to betray my own ignorance of everything Plume related. So why does Plume fallout have higher thermal inertia than the surroundings? Is it compositional, or is it more?
It's a good. We actually haven't looked too much into that. We did. I know we did a calculation in that 2010 paper where we calculated the energy of Plume impacting the surface to see if that would increase the temperature. And it doesn't. So why could be a thermal inertia variation? Could just be due to the different particle sizes on the surface.
My follow-up question would then be, because does Io have higher thermal inertia in its Plume deposits imply that other planets would have the same thermal inertia relationship?
Maybe. Is that a good answer? Maybe. I've actually been dying to figure it out for Enceladus. I keep asking some of the Cassini folks if they've looked at thermal inertias in the Plume and outside the Plume, and I haven't heard an answer.